All right. So we understood the quantum numbers that we have. The first quantum number we have is a principal quantum number represented by n, which tells you the shells, right? N is equal to 1, n is equal to 2, n is equal to 3, and like that. The second quantum number that we have is angular momentum quantum number represented by ml, which just tells you the shape of a subshell. So this is a shell, and then this is going to be talking about a subshell, its shape. All right. So we said when you have got L, ML is between negative L all the way up to positive L. For example, when n is equal to, did I say that? So that means I've given a wrong symbol for this one. So angular momentum quantum number, the symbol is L, okay, which shows the subshell. And how do you find L? L is found from 0 up to n minus 1, meaning that if you are in the first principal quantum number, L is going to just be 0. In the second principal quantum number, L is going to be 0 and 1. Third principal quantum number, L is going to be 0, 1, and 2, like that. Okay, so that is how you find L. That is the angular momentum quantum number. It just tells you of the orbitals. Okay, we said when L is equal to 0, that is an s orbital. When L is equal to 1, that's a p orbital. L is equal to 2, that's a d orbital. L is equal to 3, that's f orbital. L is equal to 4, that is a g orbital. This is what we call SPDFG. Now, from here, if they say write the electron configuration, please forget about high school, where if they say write the electron configuration, let's say for oxygen, which has got does it have 8 electrons, you say it is 2,6, so you not write 2,6. So when you say write the electron configuration, what you want to write is you write in SPDF form. All right, so that is how you get to write. Now remember, we had mentioned earlier to say for the first energy level, when you've got n is equal to 1, we said L is going to be equal to 0, right? And we said when you have got L being equal to 0, this is an s orbital. Okay, for n is equal to 2, we said L is going to be 0 and 1. When L is 0, that is s orbital. When L is 1, that is a p orbital. Okay, when n is equal to 3, we said L is going to be 0, 1, and 2. So this means that S, whenever L is 0, S, we are going to have S. When L is 1, we are going to have P. When L is 2, we are going to have D. And then for the fourth energy level, when n is equal to 4, meaning that L, the angular momentum quantum number, is going to be 0, 1, 2, and 3. Meaning that the orbitals we're going to have when L is equal to 0, that is S, L is equal to 1, that is P, L is equal to 2, that is D, L is equal to 3, that is F. For N is equal to 5, L is going to be 0, 1, 2, 3, and 4. When you have got 0 as L, that is S, 1 is P, 2 is D, 3 is F, 4 is G. Actually, we just end at G. I don't know what comes after G, right? We will end at G. And mostly you just use the SPD most of the times. Now, remember we said when L is equal to 0, that is the angular momentum quantum number being equal to 0, meaning that the magnetic quantum number, ML, the magnetic quantum number is a number that is between positive L and negative L. So if L is equal to 0, that means that the magnetic quantum number is just going to be what? There is no number between 0 and 0. That means it's just going to be 0 itself. And when you have got 0 only, this means you only have one orbital. And we said one orbital can have a maximum of 2 electrons, meaning that the s orbital can only have 2 electrons. Okay, when L is equal to 1, this is what we are calling the p orbital. So when L is equal to 1, meaning ML, which is the magnetic quantum number, is going to be from negative 1 to positive 1. Okay. When you have got these three numbers, meaning that you have got three orbitals and each orbital can have two electrons, meaning that a p orbital can have 6 electrons max. When L is equal to 2, this is what gives us the d orbital. So meaning that ML is going to be from negative 2 to positive 2. And we can see these are how many? 5 orbitals. Each orbital can have 2 electrons, meaning that the d can have 10 electrons maximum. When L is equal to 3, that is the f orbital. So we're going to have ML being from negative 3 to positive 3. That is going to give us 7 orbitals. And each orbital can have 2 electrons, meaning that in the f we're going to have 14 electrons. When L is equal to 4, that is the g orbital, meaning that we're going to have ML from negative 4 to positive 4, which gives us 9. And 9 times 2 electrons, that is going to be 18 electrons in the g orbital. Okay, so this is in the first shell. We can see we only have the s orbital, meaning that we can only have a maximum of 2 electrons in the first shell. Second shell we have got the s and the p, meaning we are going to have 2 plus 6 electrons, 8 electrons. And then in the third shell we have got spd, 2 plus 6 plus 10 electrons. That gives us 18 electrons in the third shell. We can also find in the fourth shell just like that. Right, now, yes, Martha.
So I don't. I'm sorry, sir, but I don't understand on how you are counting. How are you counting? You are confusing me a lot.
Counting how? You did you also miss the
Those
last class?
electrons. No, I was there. I didn't understand even last time.
Okay, so what we are saying is, have you understood on how to get L?
Yeah, definitely we have the formula, which is n minus 1.
Yes. So when you find L, right? When you find L, okay, this is the angular momentum quantum number. Now you need to get the magnetic quantum number. The magnetic quantum number is going to tell you the number of orbitals in a subshell, right? For example, we have got this is a shell, and then in the first shell we can see we have got this subshell. Now, how many orbitals are in this subshell? To find how many orbitals are in this subshell, that's when you use this formula. ML is between negative L and positive L. Now we can see here L is 0, right? Do you have any number between 0 and, like, you don't have any number between 0, right? You don't have the negative and the positive of 0, meaning that ML, when L is equal to 0, is just going to be 0. When you just see one number, this is an orbital, and we said an orbital can have 2 electrons. That's why I'm saying when L is equal to 0, this is the what? This is the s orbital, and that means you can only have 2 electrons, because one orbital can only accommodate 2 electrons, right? If you come to n is equal to 2, we have got L being equal to 0 and L being equal to 1. But when L is 0, we know already that that is the s orbital, and it can only have 2 electrons. Now what if when L is 1? That's when you come here. You want to find ML, which is the magnetic quantum number. That is going to determine how many orbitals are in the subshell. L is equal to 1. So we are saying you are going to get the positive and the negative of this number and all the numbers between. So saying when L is 0, okay, ML is going to, I mean when L is 1, ML is going to be from negative 1 to positive 1. Okay, from negative 1 to positive 1. And you know we have got a 0 between. So these three are saying these are the orbitals that are in the L is equal to 1. Yes, Martha.
Sir, why are you teaching me how to find the magnetic quantum number? I told you those things that you are putting on top. Okay, for the first one, I understand. The S shell only has 0 and stuff, and it can only accommodate 2 electrons. What of that 6, that 10, that 14? That's why I don't understand. I don't get those to my electrons that you are putting on top.
That's
Those are
what
the things I
that's
was saying.
that's what I'm explaining.
That's what you're explaining, but it looks like you're explaining the magnetic quantum number.
Okay, so if you know how to find ML, you can see you've got magnetic quantum number, you have found negative 1, 0, and positive 1. These things are able to see these numbers represent orbitals. So basically you have got three orbitals. In other words, when you have got L being equal to 1, you know this is a p orbital. And that means that you are going to have, in the p orbital, you have got three suborbitals. And each orbital can have two electrons, meaning this is going to have two electrons. This one, two electrons. This one, two electrons. That is the one which gives you six electrons for each p orbital. When you come to the d orbital, how did you find the d orbital? It can, whenever you see that L is equal to 2, that is going to give you a d orbital. So you find the magnetic quantum number. Magnetic quantum number is going to be from negative 2 to positive 2. How many numbers are these? 1, 2, 3, 4, 5. These are telling you these are orbitals. You have got 5 orbitals for the d orbital. So the d orbital has got 5 suborbitals, and each orbital contains 2 electrons. That's why we're able to see 10 electrons on top of d, because each d orbital is going to have 10 electrons maximum. Do you understand that?
All right, sir. Thank you so much.
Okay. Now that we have found this, we are going to put the numbers in front just to represent the energy level in which that orbital is. So this S is coming from the 1s, or from the first energy level. This is from the second energy level, third energy level, and then you have got fourth energy level. This is from the fifth energy level. All right. Now, when you have been given an atom, you want to write the electron configuration. For example, let's say they've given you oxygen. You know that oxygen has got how many electrons? It has got 8 electrons. To write the electron configuration for oxygen, there are 3 rules that you need to know. You need to know these. Okay, 3 rules that you need to know. The first one is called the Pauli's exclusion principle. I'm just going to state the definitions. You can write them if you want. Pauli's exclusion. And they are very, very important because they are going to ask you in an exam to state Pauli's exclusion principle. And without you knowing this, you'll not be able to know how to write the electron configuration. So what does Pauli's exclusion principle tell us? Pauli's exclusion principle states that no two electrons within an atom may have identical set of all four quantum numbers. In other words, you can't, if you have got the same atom, this is an atom. You remember you have got four quantum numbers, principal quantum
Sir,
number.
kindly repeat that again.
I'll repeat. Remember you have got four quantum numbers. The principal quantum number represented by n, the angular momentum quantum number represented by L, the magnetic quantum number ml, and the electron spin ms. So Pauli's exclusion principle says no two electrons in the same atom can have the same set of all the four quantum numbers. That is what this law states, or this rule or principle states. You cannot find two electrons in the same atom unless in different atoms, but you cannot find two electrons in the same atom with the same set of all the four quantum numbers. Okay? That is Pauli's exclusion principle. No two electrons in the same atom can have the same set of all the four quantum numbers. That is what it states. And because of that, Pauli's exclusion principle is also going to tell you that no two electrons in the same orbital should have the same spin. Okay? No two electrons in the same orbital should have the same spin. I don't know if you've gotten that. In other words, you can't have in the same orbital electrons going in the same direction. That is Pauli's exclusion principle. And Pauli's exclusion principle also tells us that no one orbital can be filled by more than two electrons. So I've talked about three things what the Pauli's exclusion principle is telling us. The first thing I've said, no two electrons in the same atom can have the same set of four quantum numbers. The second thing that I've said, you cannot have electrons in the same orbital having the same spin. The third thing that I've said, you cannot have more than two electrons in the same orbital. Please take note of those three things. That is the Pauli's exclusion principle. Because they can bring something and then they say what rule has been violated. So you need to know what this rule states so that you know if it is violated. Alright. Another rule that you need to know is called the Aufbau's principle. Now, what does the Aufbau's principle state? The Aufbau's principle is going to tell that electrons will occupy the lowest energy level orbitals that will receive it. In other words, when you are writing the electron configuration, the first energy levels that, I mean, the first orbitals that you need to fill are those orbitals with the lowest energy. Okay? Electrons will occupy the lowest available energy orbitals. Alright? That is what it states. Hofbau's principle, fill up low energy levels first when you are writing electron configuration. Now, how do you know which energy levels are lower than which ones? What you are going to do is you use this one. So the first one is the s orbital, it is the lowest, and then followed by the 2s orbital, which is lowest. Please follow the arrow straight the way I'm drawing it. Okay, like that, and then you are going to come like that, and then you are going to follow it. Just follow it straight as long as you drew the same way I've drawn, like that, and then you follow it like that, and then you follow it like that, meaning that when you are filling electrons in an orbital, the first one you're going to fill is the 1s. Please, when you reach the end of the arrow, begin from the beginning of the next arrow. Okay, so when you fill the 1s, and then you are going to follow it like this, and then you start, now you fill this one. After then, you are now going to follow it on top like that. You fill the 2p, and then you fill the 2s, the 3s. After that, you follow it again up like that. You are going to fill the 3p and then the 4s. After that, you follow the arrow up again like that. You fill the 3d electron, the 4p electron, the 5s, not electron but orbital. After that, you follow it up again like that. You are going to fill the 4d and then the 5p. So the way the arrow is going, that tells you which orbital has got more energy than this one, which one. So meaning that the lowest energy orbital is the 1s, followed by the 2s, followed by the 2p, followed by the 3s, followed by the 3p, and then followed by the 4s, followed by 3d, and then 4p, and then 5s, and then 4d, 5p, like that. And then you continue, you also come this side, 4f, 5d, and then you are going to come here, 5f, and then, but before the the arrows are still going, like the arrow is still going this side. So after the 5p, you are supposed to go to the 6s here. That's where the arrow is going. And then also this arrow will continue like that. I've not just written what is down there, but that is how you follow energy. Which one has got lower energy than which one? Do you have any questions? Any question?
So, so when it comes to energy levels, you
Yes.
mean 3p 3p has got less than 2p?
Okay. So look at this. So I've got 2p, right? And then you go to 3s. And then now that's when you are going to come like this. Meaning that the 3p has got more energy than the everything on top, okay? It has got higher energy. Unless if you consider the 3p has got more energy than the what? I mean has got less energy than the 4s. Okay? Even if this is an s orbital, it has got more energy than the 3p. Again, if you consider if you feel like this, you're supposed to go like that. That means that the 4s, even if it is in the fourth energy level, it has got lower energy than the 3d, even if it is in the third energy level. So in other words, the energy level will not tell you how energetic an orbital is. This one is more outside the 4s, the 3d is inside, but 3d has got higher energy than the 4s. Okay, is that okay?
Yeah, it's fine. Thank you.
Okay, the last rule that you need to know. Remember, of Bohr's exclusion principle is telling you of how you are supposed to put electrons. Okay, you are saying no to, yes.
Sorry, sir. And I didn't get when you talked about the off balls. I don't know if it's off balls or what. Yeah, the principle. I didn't even get. I
So
just heard the explanation. Mhm.
the of Bohr's principle states that when filling up electrons in orbitals, electrons will occupy the lowest available energy orbitals before occupying higher ones. You can put it in any word, as long as what you're talking about is when you are filling up orbitals, first fill those which have got lower energy, and then you can fill those with higher energy. That is what Hofbauer's principle talks about. Good.
Yes, sir.
All right, and then the next one you need to know is called Hand's rule. Hand's rule. Now, what does Hand's rule tell us? Hand's rule is going to tell you about electrons. When you are filling up electrons in an orbital, okay, electrons will occupy all orbitals in a subshell with a single electron having parallel spins before you can occupy them doubly. In other words, electrons go to their own orbital before they fill up an occupied orbital. So if you have got like the p orbital which has got three suborbitals like this, when you are filling up this orbital according to Hand's rule, first fill them singly before you can fill them doubly. Okay? We say for degenerate orbitals, if you hear the word degenerate, meaning that they've got the same energy. Okay, like these all come from the p orbital, so meaning that all these orbitals, the px, the py, and the pz, they've got the same energy. They are called degenerate. So when of Andy's rule says that for degenerate orbitals, electrons are going to fill them singly before filling them doubly. Okay, electrons are going to fill them singly before filling them doubly. So if I've got four electrons, I am filling it, I'm supposed to first fill this one up, I go also to this one up, I go to this one up, I'll remain with one electron, and then that one electron I come like this. I'll start now filling with an opposite spin. If I fill it with the up spin, okay, if I put like this, if you see in the same orbit I've put like that, and then I again put like this, you need to know that I've violated a rule. And that rule I've violated is Pauli's exclusion principle. I have violated Pauli's exclusion principle. Why? Because an orbital can't have two electrons with the same spin. So if you see I've got four electrons and then I'll field like this, you should just know that I have violated Hand's rule. Why? Because I cannot fill these two orbitals before I fill this last one. So I should be filling them singly. Okay? I fill them singly and they should have the same spin. And then the electron that remains, I start again. It should have opposite spins. Okay? It should point in the opposite direction. So then I have followed Hand's rule. Are we okay?
Yes, sir. Thank you. And it's the only principle that is easy.
They are all easy. We are going to understand. Okay. So now that you have talked about all these principles, let's now write the electron configuration for different atoms. Please, you can pick just random atoms you give us, and then we are going to be able to fill them. Okay. So the first one that we are going to, can you give me any atom, especially those which have got lower proton numbers before we go to those with higher proton numbers? Any atom?
I start with oxygen.
as long as you know its proton number. Okay, oxygen has got 8, right? A proton number of
Yes, it
8.
has eight.
All right. Now, when you are feeding, remember the rules that you are following, all the rules you are supposed to follow them. So first three, I'm going to write the orbitals. Okay, I'm going to write the orbital starting with the lowest available energy orbital, that is the 1s. So I'm going to write this orbital down here. This is the 1s orbital, and then I'm going to go to the next low energy orbital, which is the 2s. I'm going to write them on the straight line. This is the 2s, and then I'm going to go to the next one I'm supposed to fill is the 2p. Now for the 2p, remember it has got 3 suborbitals. That is why I've got 6 electrons on top of that, because I've got 3 suborbitals. So for this one, I'm going to write it more. It's going to be a bit different. So I can even move it. Can even move it to start from here. So this is going to be the 2p. Okay, now I've written it. I can start filling the electrons. Okay, starting with off-Bohr's principle. Off-Bohr, remember, says when filling up electrons, start filling those orbitals with lowest available energy. So I'm going to start with the 1s. I'm going to put an electron first. Okay, lowest available energy, you are going to fill it all. So I'm going to fill it all, and then I'm going to go to the higher energy orbital, which is the 2s. I'm going to fill it all. So I've used 4 electrons. From the 8, we are remaining with 4. And then we are going to go to the 2p. But remember, the 2p is degenerate. Okay, it's degenerate, meaning that you have got 3 suborbitals which have got the same energy. Now again, as we were filling this, you've seen I've only filled them with 2 electrons, meaning that I've obeyed Pauli's exclusion principle. Okay, only 2 electrons in an orbital, and they are all having opposite spins, meaning I've obeyed Pauli's exclusion principle. Yes, is there a question? Is there a
I
question?
can I can't understand anything you're doing there.
You can't understand anything. Why can't you understand? Where are you behind? Where are you behind?
The way you're putting those, I don't know if they are rectangles, then putting those arrows.
I've just put orbitals. Just start from down writing orbitals. You already know, I've already said which ones have got lower energy than which ones. The lowest available energy orbital is the 1s, followed by the 2s, and then you have got the 2p, followed by the 3s. So just write those. Now, you already know that the s orbital only has one orbital. That is why for the s, I'm just writing 1. After I write the 1s, I'm now supposed to write the 2s. That is the next orbital. After I write that one, I'm now supposed to write the 2p. Now the 2p, you've seen it can be filled by maximum of 6 electrons. I already said, for how did you find the 6 electrons? Because we had 3 orbitals, and each orbital can be occupied by 2 electrons. This is why you are able to see I've written 3 here. Okay, that is the 2p. And then after the 2p, I was supposed to write the 3s, but I know that I can fill oxygen with only these orbitals without the 3s. Are you still lost? Are you still lost?
No,
But how did you know?
Can you repeat that?
I was saying, I don't know. I'm saying, how did you know that you're not going to have the other one, the 3s? Because daily oxygen has
Okay, l-
28 electrons,
like just look at
and they're supposed
just look at this. This one will have 2 electrons. This one will have 2 electrons. 2 electrons. 2 electrons. 2 electrons. How many electrons do you get there? How many is it giving you?
oh, okay, so I didn't get properly. Thank you.
Paxina, you also had a question.
Yes.
All right. So now, according to Pauli's exclusion principle, in one orbital we cannot have more than two electrons, and the electrons which are there should have opposite spins. Okay. Now we are going to use Hofbau's principle. Hofbau's principle says first few electrons having the lowest available energy. That's why I'm filling the 1s. Please first fill them up. They should have two electrons, one up spin, another one down spin. And then you go to the 2s, one up spin, one down spin. Okay, and then now you go to the 2p. Now the 2p are degenerate, and remember, for degenerate orbitals we talked about the Hans rule. First fill them singly before filling them doubly. Now from the 8 we have already used 4 electrons, so we are remaining with 4, so that would be 1, 2, 3, and then we write the fourth one here. So we have filled, this is the orbital diagram. This is called the orbital diagram for oxygen, but the electron configuration for oxygen is going to be, you start with the 1s. Okay, the 1s orbital can accommodate a maximum of two electrons. We're going to put a 2 on top, and then we go to the 2s orbital. Okay, that is 2s. That the s also can accommodate a maximum of two electrons. We put a 2 on top. After the 2s, we're supposed to go to the 2p. Okay, you write 2p. You know that p can accommodate a maximum of 6 electrons, but you've already filled 2 electrons from the, I mean 4 electrons from the 8. You're only remaining with 4, so don't have a choice but to put 4 here. Okay, but remember, the P can have a maximum of 6 electrons, but you only have 4. Where do you get the other 2? You don't have a choice but just to put 4 there. Are we okay? Anyone who is left out? Okay, you can give me another element. Another element.
So before we go any further, kindly define degenerate electrons.
Degenerate orbitals. Degenerate means having the same energy. If you see orbitals like this, they are all p orbitals, but there are three of them suborbitals. Those are degenerate, having the same energy. Is it okay?
Yes, it's okay.
Okay, you can give me another atom, any, I mean another element with its proton number. You don't know?
Okay, sir.
Yeah.
Sodium.
What's its proton number? You don't know?
I've forgotten. I've forgotten.
Its proton number is 11. Anyway, you always be given a periodic table. So to write the electron configuration for this atom, first let me write the orbital diagram. Always start with the 1s orbital. Okay, let's start with the electron configuration. Okay, so the electron configuration, you always start with the 1s. So the 1s can have two electrons. Yes, there is a hand.
I was suggesting, yes.
Yes.
I was suggesting if you could erase those one is shanshan, and then you start, you start sodium, and then maybe that you will get what you're doing.
Which one should I erase?
Those you are getting one is two SP, those.
But if I erase them, where will I get them?
Yeah, you start now doing the process.
Alright. Whenever you want to fill up orbitals, please you need to know it.
Excuse me. Sir, okay, sir, you've removed them now. Me, how am I going to be knowing which one is big, which one is what? So that's
I'll write, don't worry. Okay, whenever you want to fill up orbitals, please you need to know this in mind. You first need to have the 1s orbital, and then down you're going to have the 2s, okay, you are going to have the 3s, you are going to have the 4s, you are going to have the 5s, you are going to have the 6s, just like that. After the s, you are going to have the p, but just know that the first energy level doesn't have any p orbital, so it only starts here. 2p, you are going to have 3p, you are going to have 4p, you are going to have 5p, you are going to have 6p. And then the next orbital is d. Just know that the second energy level doesn't have the d orbital. Okay, so the d only starts from the 3. So you are going to have 3d, you are going to have 4d, 3d, you are going to have 4d, you are going to have 5d, you are going to have 6d. The next orbital is the f. Just know that the 3 doesn't have f. Okay, that means you are going to start from the 4f, and then 5f, and then 6f. The next one is supposed to be g, but for the fourth energy level you don't have g. It's supposed to start from 5g. I don't know if you've gotten that now.
Yes.
Okay, and every time you are filling up these orbitals, please, you need to know uh, the arrow, like it goes like this. This is the lowest available energy, the next lowest available energy. Write them straight, okay, like that, and then it comes like this. I can put them much better, like that. Then we are going to have like this, we are going to have that, and then you are going to have that, just straight. You are going to have that, you are going to have also this, like that. So that will tell you how energy gets to move. So the lowest available energy, 1s, followed by 2p, I mean 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. You go to 4f, 5d, 6p, 5f, and then 6d. You also need to know the maximum electrons that each orbital can occupy. Any s orbital, the maximum electrons it can have is 2. Any p orbital, the maximum electron it can have is 6. Any d orbital, the maximum electron it can have is 10. Any f orbital, the maximum electron it can have is 14. We already determined that. Okay, so are we okay here now? Are we okay?
Yes.
Now let's write the electron configuration for sodium, which has got a proton number of 11. So we are saying when you start filling this, always according to Aufbau's principle, fill lower energy orbitals before filling higher ones. So I've got the 1s, right? So we're going to start with the 1s orbital with 2 electrons. That's the maximum it can hold. After the 1s, you go now to the 2s with also 2 electrons. That's the maximum it can hold. After the 2s, the next one supposed to fill is the 2p, not the 3s, please. Okay, you go to the 2p. Now the maximum a p orbital can hold is 6 electrons. So if you have available electrons, like you've used up 2 plus 2, that is 4, you've used up 4 from the 11, how many are remaining? Is it 7? Okay, meaning that we have 7 electrons which are remaining. So the 6 can be accommodated by the 2p orbital, and then 1 electron that has remained now can go into the 3s. That will be 3s with a 1 electron. Are we okay? Are we okay?
Yes.
Okay, now if you write the electron configuration, an orbital diagram will be very, very easy to write. So always start with the lowest available energy, that is the 1s, and then you go to the next one, which is the 2s, and then you go to the next one. Now the next one is supposed to be 2p, as we've seen. That's the next one you feel, but this one has got 3 suborbitals. That is the 2p. After the 2p, the next one is supposed to fill is the 3s. Now the 3s, I'm going to write it in the same line as the 1s and the 2s. the 3s. Okay, when I write this now, I'll start filling. Remember, I've got 11 electrons. First few lower energy orbitals, according to Pauli's exclusion principle, they should have opposite spins. According to to Hofbauer's rule, first few lower energy orbitals. If you come to the two p, these are degenerate, so first fill them singly. So remember, we filled 2, 4. You'll be counting 4, 5, 6, 7, 8, 9, 10, and then the 11th one. Now you jump to a higher energy orbital. This is the orbital diagram for sodium. Are we okay? Are we okay? Yes, go on.
Yeah, so why I'm putting the S orbital, the three S orbital in the same line, is it a rule that it should be there as well?
Yeah, like you think of it, they are all s orbitals, so that's why I've just decided to put them in the same line.
Yeah, okay.
All right, so we can pick another element. Let me choose another element, maybe something that has got a a lot of electrons. What element do you know that has got a lot of electrons? Let's try phosphorus. Okay, so phosphorus has got 15. That's not too much. I can get copper. Okay, copper has got 29 electrons. Let's try to use it. Now it will be difficult for me to write the orbital diagram because it will be so long. If you just know how to write the electron configuration, it will be very easy to write the orbital diagram because you just need to put orbitals. Okay, you know that the 3D is going to have 5 suborbitals. So for the 3D or any d orbital, they're supposed to be 5. You divide 5 of them, and then you are going to be filling them singly. So orbital diagrams are so easy if you know already the electron configuration. So I've got now I don't want to use copper. I don't want to use copper. Okay, let me keep copper. Here it has got 29. Okay, what else can I keep which are important for us? Even chromium. Let me just find the proton number for chromium. These two, please, you need to know they are the special ones. Actually, they even like them. Okay, chromium has got 24. All right, like that. So I can pick anything else. Let me pick, I can pick gold. Now gold has got 79. That is like too much. That is way too much. It's going to take up our space. What of silver? Okay, at least we can use silver, which has got 47. What element is this? Ag. What element is this? All right. So let's start filling it. The first, remember, always first fill the lower energy uh, orbital. So we're going to fill 1s with 2 electrons. And then we go to the 2s with 2 electrons. Be following, please, from here. Okay, from the 2s, you should be telling me what I should fill next. What should I fill? What should I fill? Which orbital?
2p,
With how many electrons?
6,
6. Okay, from the 2p, what should I fill?
3s,
Okay, with how many electrons?
2,
Okay, from the 3s, what should I fill?
3b,
3p. With how many electrons?
6,
6. And then from the 3p,
4s,
4s. With how many electrons?
3D. You have skipped. You have skipped, sir.
No, from the 3p, you go down. You don't go to the 3D.
Why?
Follow the arrow, please. You go like this, you follow the arrow like down so. When you reach here, and then you go again up.
Oh,
So we have filled the 4s, now we go and fill the 3d. How many electrons? How many?
10.
10 electrons. Now we shouldn't go on and on. Okay? We shouldn't go on and on with filling. So from here first, let me count. I see how many electrons I've used because we can go beyond. So this is 2, 4, 10, 12, 18, 20, 30. So we have filled 30 electrons. We're only remaining with the 17 electrons. Okay, so we're remaining with 17 electrons. Please be counting what you'll be removing. So from the 3D, what are we supposed to fill? Fro-
Copy.
okay, that will be 4p with 6 electrons. From remember from 17 we have removed 6, we are remaining with 7. I mean we are remaining with 11. And then from the 4p, what are we supposed to fill?
5S.
5s, that is with 2 electrons, so we are remaining with the 9 electrons. All right, and then from the 5s, what are we supposed to fill?
4D.
4d. Uh-huh, 4d with how many electrons?
12.
How many electrons?
12.
No, 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 remember we're only remaining with 9 electrons, so we are going to put all the 9. Okay, we're going to put all the 9. Remember, a d orbital can have a maximum of 10 electrons, but we only have 9. So we're just going to put 9 there. This is how we get to write the legend configuration. It doesn't matter how long an atom is. I mean, how big an atom is. Do we have questions?
So, will these things come in the exam?
They're actually going to bring for you to write the legend configuration.
No, sir, me, I'm lost. The way you are getting the what? You are skipping it. I don't know if you are skipping it or you were. Oh, I don't know.
Where are you lost?
The way you are skipping from. Then you got from 3P6C, you go to 4C, and then
Okay.
3D.
Okay. Have you seen how the arrows are moving? Have you seen how the arrows are moving?
Yes.
So when you are writing the lighting configuration, you are going to follow the arrows like where one arrow ends. Okay? You are going to
Mm-hmm.
connect to the beginning of another arrow. Where one arrow ends, you connect to the beginning of another arrow. Where one ends, you connect to the beginning of another one. Where one ends, just like that. So that's how you are going to be moving.
Mm,
It's okay?
okay.
All right. Now, most of the times in your exams, if you check the way they are going to bring, they are going to ask you to write a shorthand form electron configuration, not a long, not this one which I've written here. This is the long form. But if they have not specified, you can write whatsoever you decide to which one which is easier for you. Okay, but mostly in the papers you're going to be seeing, at least what I've seen most of the times, they are going to ask you to write a shorthand form or the shorthand electron configuration. Okay, which is now for you to be able to write that, you need first to visualize how a periodic table is. I'll just try to see if I'm able to sketch. It's not it, but just a sketch of the periodic table. Okay, so here is a sketch of the periodic table. What do we call these elements which are here? What do,
Transition elements.
yeah, they are transition metals. All right, they are transition metals. Okay. Now we have got these different groups. I'm going to put them in different colors. So I'm going to split. We have got this group this side. We have got this group on the middle. These are different groups. Okay. So the first one that is group 1 and group 2. These we call them this block we call it the S block. Okay, this is the S block. Depending with the group number. This is this depending with the period number that will determine what period we are going to have. Like on top here, this is where I've got hydrogen, right? So that is going to be the 1s, and then second that is going to be the 2s, and then third 3s, just like that. So this is basically called the S block. So we're going to have 1s, 2s, 3s, 4s, 5s. It ends up to 7s. Like you have got seven periods going down. So this is basically called the S block. Okay, you need to know that is where you have got a 1s. Now how do you tell one? You just start from the top, like the first one which is on top there where hydrogen is. That is the period 1 is going to be where the 1s is going to be. Period 2, the 2s. So this is called the S block. Okay, the S block. And then at the end there, that is where we're going to see the P block. Okay, that is where we're going to see the P block. Now remember, even when you are writing, you only have one S, right? But you don't have one P. Okay, you don't have one P. Because of this, on top here, like this element which is found here, which is hydrogen, here we know we have got helium, right? On top here we don't have, even if this helium is this side, it doesn't have any P. Like helium only has got two electrons, so it doesn't have anything like P. You can't have one P. So for the P, they only start from 2. Okay, for the S we start from 1s, 2s, but for the P, as we have said, we only have 2p, right? And then 3p, and then 4p, like that. We don't have 1p. So that is why the first group, the first period here is going to be the 2p, and then the next one is going to be the 3p. The next one like that is going to be the 4p. The next one like that is going to be the 5p, and you continue to go like that. Okay, and then so this is the P block, and then this block here is called the D block. Now again, you can see here we don't, there's no such a thing as 2D. There's no 2D. That means that the one which is on top very much here is called the 3D. You don't have anything called 2D. Okay, you don't have such an orbital. So please, you need to know these blocks. This is a S block, this is a D block, this is a P block. So when you are writing the shorthand form electron configuration, what you are going to do is, for example, we can look at sulfur. Let me first find out how many electrons sulfur has. Or maybe you can tell us the proton number. Okay, the proton number for sulfur is 16. Now we want to write the shorthand electron configuration for sulfur. What you are going to do is you are going to go on the periodic table. Okay, you are going to go on the periodic table. So if you just look at this proton number of 16, where do you expect the sulfur to be? If you write the electron configuration that you have always known, it is going to be 2, 8, what, 6. You can see these are 3, right? Meaning that it is in the third period. So sulfur is in period 3. Okay, if you have got period 1, period 2, so sulfur is somewhere in this period 3. And then because you can see it ends with a 6 at the end, it means it is in group 6. Okay, this is going to be group 8. This is going to be group something like 7, Group 6 will be somewhere here. I'm not writing properly. So sulfur is going to be like here in group 6 and then period 3. Okay, so to write the short form electron configuration for sulfur, what we are going to do is we are going to look at the noble gas that comes before sulfur. The noble gas that comes before sulfur. Now, sulfur is in period 3, so we are going to look at period 2. That is the noble gas. Noble gases are these elements which are in group 8. So we are going to come in group 8, just the group before group 3 where sulfur is, that is group 2. So the noble gas that we are going to see here, that is neon, right? There is neon here. And how many electrons do you expect to find in neon? Since it's in period 2, is this even 3 where I've put this one? Because period 1 is supposed to be here, period 2 is supposed to be here. Okay, period 3 is supposed to be here. So I forgot that there is period 1. Period 1 is supposed to be actually on top. So sulfur is going to be somewhere here. Alright. It's in the same group as oxygen. Oxygen is just on top. Okay, so the noble gas, remember on top here, the noble gas that we have, the first noble gas is helium. The next noble gas is neon. The next one, that should be argon. Now this one, remember noble gases have got a stable electron configuration, meaning that all the orbitals have been completely filled up. That's why we say they are reactive, because all the orbitals have been filled up. So you look at the noble gas before before sulfur, that is the neon. Now, if you just check on the periodic table, it will be provided. How many electrons are in neon? There are 10 electrons. Okay, like the electron configuration is 2,8. The outermost shell is completely filled up. So neon has got 10 electrons. So to write the shorthand electron configuration for sulfur, this is going to be equal to, first I'm going to write the noble gas that comes before sulfur, that is neon. I'm going to put it in these brackets. We're able to see like that. Okay, I'm going to put it like that. Now, when I do this, I already know that neon contains 10 electrons. That means that from this cysteine, I've already removed 10 electrons. I've already removed 10 electrons. How many electrons are remaining? Only 6 electrons are remaining. Now, after that, the next orbital that I always need to fill is I'm going to fill the s orbital. Okay, I'm going to fill the s orbital. Now, ask yourself, in which group is the sulfur? In which s group is sulfur? So, if you continue this thing like this, like that, okay, this is where group 1 is, this is where group 2 is, this is where group 3 is. So this is obviously the what? The 3s. So I'm going to put 3s, and you know that s should always have a maximum of how many? 2 electrons. So I'm going to put 2 on top. And then, because sulfur is in a p block, I'm supposed to put p. Now, in which p block? Remember, this is the 2, this one is the 2p, right? And then this is the 3p. We don't have 1p. Okay, that's the 3p. So meaning that we are going to have 3p there. Now remember, we only had 6 electrons which had remained. So we are going to compare the 3s and the 3p on just this table which is here. 3s, 3p. The one which was supposed to be filled first is the 3s. And I've done well by filling it first. And then now we can fill the 3p. Now, how many electrons are remaining from the 6? We've used 2. Only 4 electrons are remaining. So those are the ones we're going to put here. So this is the short form electron configuration for sulfur. That is how you write it. We are good? Are we okay? Alright. So basically that is it. That is how you get to write that. Okay.